Hi guys, I just wanted to show you the asteroid question quickly. These are my very bad drawings that I made about it. And if you've read the question, which you should have before listening to this, you've got an asteroid that's moving its way along at the blue line over there. At t equals 0 it could be there, at t equals 1 it could be here. Here's a little space station and it's looking at the asteroid as it moves along. Here's the origin, which is the center of the Earth, and you have vectors from the center of the Earth to the space station and from the center of the Earth to the asteroid locations. So the first question is, find the position vector of the asteroid relative to the space station. So it's asking for this black line here. Now then it becomes a simple triangle vector thing, and it becomes that is the new origin, if you like. So if you're talking about that, then you are saying it is SO plus OR1. Now that one is pretty straightforward, and you have that over here. And the distance as well, which is required, that one is pretty straightforward as well, 2 root 2. So we know the vector from the space station to R1, and we know its distance. Moving down, it asks to find a general expression for the distance between the asteroid and the space station at time t. So I have to do the same thing, which is subtracting two vectors to find the expression for the third part of the triangle, just like I found up there, and then take the modulus. So instead of substituting t equals to 1 into the asteroid path vector equation, I just use it generally. I subtract it, I come up with this, and then I take the modulus, which looks a bit horrible, but then works very quickly to a general expression there. Now obviously the closest it is when t is equal to 0. Even if t is equal to -1, for example, that's because of the square root, that's going to give you a larger answer. So the smallest one is when t is equal to 0. So I get that as the answer for the shortest distance. Finally, part D. Now this one takes a bit of thinking. I've put R1 here and R2 here, and the guy at the space station fires a missile when he sees the asteroid at R1. So he sees the asteroid at R1. He obviously fires it not at that position, because if he fires it there, the asteroid would have moved off by the time the missile reaches that location. So he wants to know where the asteroid will be at t equals to 2. And he wants to know the bearing from where he sees the asteroid to where the asteroid will be. So he needs to find that angle theta in green. So what we've done here is find that blue line there, which we know it's 2 root 2. And the same thing we do for over there, SR2. So we can see that that's going down there, and it comes to 5 root 2. So we know that 5 root 2 is the length of SR2. Now, what we've done is then we've taken the dot product of both the blue arms, and we've come up with 18. So we've taken it directly from the vectors. Now we know there are two ways to get dot product. It is A dot B is equal to multiplying their components together and adding them up, which is what we've done here, or it's equal to modulus A times modulus B cosine of the angle in between. So we do both these things for use both these methods and equate them. So this is A dot B using the vectors and multiplying the components, and this is A dot B using mod A mod B cosine theta. Why have we done that? Because we want to find cosine theta, but we can't find cosine theta using this setup here, unless we find, what we could do otherwise to take another straight line from there, find out that vector, and then use the triangle and maybe the cosine rule or something and get the angle. Too much trouble. What we have done instead is saying that, that mod A times mod B cosine theta is 18. I know modulus A, I know modulus B, therefore I can find theta, the angle in green, in between, just by comparing two different ways of finding the dot product of the two blue lines. Okay?